Hi again, welcome to another review session for Calculus 3208 for your final exam. Presented by CDLI as always, and we're getting close to being able to do some calculus with inverse trig functions. One more session on inverse trig, and then we'll jump into that. So here's what we're after here. We are after evaluating composite inverse trig functions. We did some of that in the last session, but only when the two functions were really the same, just inverses of one another. Now we're looking at what happens if they are not trig functions that are the same. So for instance, it says here, I want to evaluate composite expressions of a trig function and the inverse of another one. So stuff like cosine inverse of sine of something, that sort of thing, when they don't have the same nature. All right, let's get down to beeswax business. So how do we deal with f of g inverse or f inverse of g when f and g are different trig functions? Well, let's see. When it comes to dealing with special angles, so if it's stuff we recognize, then it's not a big deal. We can do it the same way that we did when we had inverse trig functions and regular trig functions that were the same thing. But when we mix them up, as long as they're special angles, it's no big deal. So let's try this first one. It says, what's the inverse cosine of negative root 2 over 2? And then we want to evaluate the sine of that. So let's start by looking where cosine is going to be equal to negative root 2 over 2. And there will be two places on our unit circle, both of them over here. Only one of those is going to be within our principal value range for cosine, though, and it's this one up here. So that gives us an angle of 3/4 of pi. So we're at 3 pi over 4. And then we want to evaluate sine of that angle, 3 pi over 4. And so the sine of 3 pi over 4 is actually the y-coordinate here, so it's positive root 2 over 2. Okay, so that's not so bad. Let's try the next one. Inverse cosine of sine of 8 pi over 3. Well, 8 pi over 3 is beyond our 0 to 2 pi business, so we've got to figure out where that is or give us something coterminal with it that puts us in a decent place. So let's see. 8 pi over 3 is actually 2 pi plus another 2 pi over 3, because 2 pi would be 6 pi over 3. So if I start from 0, 0, and I want to rotate my terminal arm, I'm going to end up in the position of 2 pi over 3. So that's right about there, okay? So we're in that basic position, and if we want to figure out what sine is for that, sine is the y-coordinate, so that's positive root 3 over 2. So now I have to evaluate the inverse cosine of positive root 3 over 2. So where would I get positive root 3 over 2, for inverse cosine? Well, there's two places where cosine is positive root 3 over 2, and they're in these two locations. And only one of those is inside the principal value range for cosine, and that's an angle of pi over 6. So each of those trig functions took us in a very different direction that time, but we're able to work that out no problem. So with special angles, everything is hunky-dory. Let's make it complicated. If I have to do this stuff, and I'm dealing with an angle that's not a special angle, well, first of all, I can't do the issue, unless I'm using a calculator or something, I can't do the issue where the original function is on the inside and the inverse is on the outside. I can't do that one because it doesn't work. I've got to go this way, where only the inverse is on the inside. And if I do that, then what I do is I take the ratio I have, and I have to sort of construct a triangle that would work for that ratio. So if cosine is equal to, inverse cosine of 5 over 13 means that the cosine of that special angle, particular angle, is 5 over 13. And remember, cosine is your adjacent side divided by your hypotenuse. So if I'm going to do that, I've got to put the adjacent here would have to be 5 units long, and the hypotenuse would have to be 13 units long. Okay, so let's put this to be 5. We'll say that our angle theta is right here, and then we'll say that this hypotenuse could be 13. And if that's the case, I can figure out what this missing side is down here, and that'll tell me what this angle theta is for which inverse cosine of 5 over 13 gives me the answer. So let's see. This side over here, let's Pythagorean theorem. So it's going to be the square root of 169 minus 25, which is the square root of 144, or 12. Okay, so the opposite side to that angle is 12. So now that I have all three sides of my triangle, I can find the sine ratio. The sine ratio is the opposite over the hypotenuse, 12/13. And we can do something very similar here with the cosine. Cosine of inverse tan of 7/6. So we've got to have tan being 7/6. So tan is going to be opposite over adjacent. So I'll pick the slightly longer side there to be my 7, and then the slightly shorter side to be my 6. So that means that my tan would have to be this, referring to this angle down here. So here I know that theta is equal to the inverse tan of 7/6. Okay, so let's figure out what the next side would have to be. How big is that hypotenuse? Well, it's going to be the square root of 36 plus 49, which by my estimation is the square root of about 85. Wow, that's a pretty big number. Square root of 85 is the length of that side. Well, I don't even know. Can we simplify the square root of 85? I don't think so. So what we'll do then is we will evaluate the cosine for this particular triangle. So for this angle that we marked down here, theta, the cosine is going to be the adjacent side divided by the hypotenuse. So that's going to be 6 over root 85. And nobody likes a radical in the denominator. So we're going to have 6 root 85 over 85 if we rationalize. So there is our cosine of the inverse tan of 7/6. Funny stuff, but that's what we've got to do to get an exact value. All right, we mosey along. Here's a test question. Evaluate tan of the inverse cosine of 7/11. So the first thing I'm going to do is construct a right triangle. So to construct a right triangle, I don't know how proportional or to scale this is going to be, but I don't really care because it'll work anyway. So here's my right triangle, and then I'm going to label up some sides on here. So cosine, I know the hypotenuse is going to be 11, and then one of the other sides is going to be 7. I don't even know if that's the right side, but we'll find out shortly. So this missing side down here will have to be the square root of 11 squared, which is 121, minus 7 squared, which is 49. So let's see. 121 minus 49 by my mental arithmetic is about 72. So this is the square root of 72. Now that's going to reduce because root 72 is 6 root 2. So we've got this side over here to be 6 root 2. Okay. Now what we have to remember is this was our adjacent and this was our hypotenuse. So our angle theta is right here. So if I want to get the tangent, it's going to be the opposite over the adjacent now. So the tan of that angle, which was the inverse cosine of 7/11, and that's going to give us 6 root 2 divided by 7. Okay, good stuff. Let's try this one. Find the exact value of, whoa, this is scary. Whew, take a deep breath, we can do it. All right, what I'm seeing here is A and B. And when I see A and B added together inside a cosine, I think, oh my goodness, they're going to make me use a sum identity for a compound angle, and yeah, that's right, we've got to do it. So cosine of A plus B, let's remember our formula. The cosine of A and B is cosine A, cosine B, minus sine A, sine B. Okay, so what we have here is cosine of the inverse tan of 2 times the cosine of the inverse tan of 3. Okay, got you so far. And then to that, from that, I've got to subtract. I'm not going to get space. Let's put it right below it. So I have to subtract the sine of both of those things again. So inverse tan of 2 and multiplied by the sine of the inverse tan of 3. Okay, that looks lovely. So to figure all that out, I've got to construct 2 different triangles. One where the tan of a particular angle gives me a value of 2, and one where the tan gives me a value of 3. But they're not fractions. So we'll make them fractions. So we'll say all of these things are over 1, and then we've got some nice fractions kicking around. Okay. So let's do our first triangle. Now I'm just going to rough this one out freehand because we got the idea now. So tan is going to be equal to 2 over 1, so opposite over adjacent. So there's the longer side. We'll call that, that, and that, and then there's going to be our theta. Okay, so this side is going to be the square root of 2 squared plus 1 squared, which is the square root of 5. Okay, so that tells me that that's going to work for the first triangle. Let's do one triangle for the other one as well, and then we'll put it all together at the same time. So for the other triangle, I have to have a 3 and a 1 for my opposite and adjacent. And so that angle, let's call it alpha or something, has to be up there. So we're going to have the square root of 1 squared plus 3 squared, which is the square root of 10. Okay, so what that tells me is that the cosine of the angle that has the 2 on its triangle is going to be equal to 1 over square root 5. So I've got the cosine business here. This one is going to be 1 over square root 5. And the cosine of the angle that has the 3 on its triangle is going to be 1 over the square root of 10. Okay, so we're getting somewhere now. And then I have to subtract. The sine of the angle with the 2 on the triangle is going to be 2 over root 5. 2 over square root 5. And the sine of the angle that has the 3 on its triangle is going to be 3 over square root 10. So that's multiplied by 3 over square root 10. Okay, so the first triangle, or the first fraction, excuse me, gives me 1 over root 50. Subtract 6 over root 50. And instead of having to rationalize those independently, since they have a common denominator, I know that that's negative 5 over the square root of 50. So I'll rationalize that just once, and that's going to give me negative 5 root 50 over 50, which is going to simplify to give us negative, let's see, 5 over 50 reduces to 1 over 10. So that's negative root 50 over 10. And that is the value of this ugly monstrosity. Wow, did you enjoy that? I know I did. Tricky questions are always lots of fun. So let's mosey along here and take a look at what's coming next. Oh, it's the your turn question. So in this case, you got to find the exact value of sine of 2 inverse tan of the square root of 2. That doesn't look particularly easy, but I'm going to give you a hint for that one. Yeah, I know you like it. I'm going to give you hints. It makes life easier for you. So let's write this out. Let's say that if tan of inverse, or the inverse tan of square root 2 is your angle, then the hint I'm going to give you here is look at the double angle formula for sine. Sine of 2 theta. And remember that that's actually just 2 sine theta cosine theta. At least in this one, you're only going to have to use one special triangle, or draw one triangle to help you. Okay? So see if you can figure that out. There's a hint. Get you through it. And I'm going to jump to the solution slide now. So here's the solution for that one. And when we do that, you can see that we did actually use that expansion here. Works out to give you a nice answer like 2 root 2 all divided by 3. Okay, so we'll move along from there then, and we'll take a look at some of the key ideas of the things that we talked about in this session. So some of our key ideas. It says we can evaluate inverse trig functions, f of the inverse of something else, or f inverse of the original g, that's something else, when they are different trig functions. When the angle in question is a special angle, we simply work from the inside out. Good. When the angle is not a special angle, we can only get exact values for this particular case, where the function that's on the inside is the inverse function. If they're flipped around, we can still do it. We just have to take a decimal approximation. With our methodologies at this point anyway, we don't really have a way to deal with that. So it's only when the inside function is the inverse that we're going to end up getting exact values for this kind of stuff. So to evaluate in that last case, remember what we do is we construct a triangle, so an appropriate right triangle to determine the correct ratio. And when you construct those triangles, it's something very similar to what you would have done in Math 2200 or Math 3200. You just sort of put that stuff together based on how it works when you have opposite and adjacent, or opposite hypotenuse, all those sorts of things. But anyway, you know all that. So good luck studying. I hope it's going well. I hope this was helpful. And I hope that you're going to do well on your exam. And if you have any questions, don't hesitate to post them up on D2L. Thank you.